Because of the all or none character of nervous activity, neural events and the relations among them can be treated by means of compositional logic. This abstract is part of an abstract from an early work. Absolutely beautiful piece of uh, scientific work that came out in the 1940s, right? 1943. I was not able to pull up the original paper, but this is a reprint from 1990s there about. But the original paper was written by a logician and a biophysicist, and it was part of the, let's see if I get that right, it's part of the Bulletin of Mathematical Biophysics in 1943. It's remarkable because it does a few things. It had been known for a while that nervous activity had some electrical properties associated with it, that the neurons, in fact, was doing something interesting using electrical signals. This has been known for a while. 1700s, people were stimulating neurons with electrical impulses and seeing muscles twitch and all of that. What they did was try and model what was happening in the neuron, build a dynamical systems model, if you will, or a functional approximation model, and then make the argument that you can tie all of that to propositional logic. It's incredible insight. It was not a complicated model. It was basically saying what the neuron does is simply accumulates all of this input. If it happens close enough in time, you can ignore the temporal components, and then it checks to see if this accumulated information crosses some threshold or not. That was it. And if it does, it fires, it becomes active. If not, it does not, and that's what's captured by the all or none character that they mentioned there. And it turns out you could do a lot of stuff if you just had this threshold gate. As entire volumes written, this is one of the most fascinating books to read. This is from 1990s. It's called Discrete Neural Computation. It says if you're given a bunch of threshold gates, you can approximate a whole bunch of functions. You can do fascinating computation. There's no learning associated with any of this. This is just simply saying that the neuron model, if you assume a threshold gate, you can do a lot of stuff. So what I'm going to do today is I'm Srideep Musuvathy, and I manage the Cognitive and Emerging Computing department. We think about the future of computing at Sandia. This is one of the things we do, is start building on those ideas that started in the 1940s and argue that a lot of these inspirational ideas are not new, but that there's a lot more we can do, and there are certain challenges associating with how to do this. I'm going to focus on looking to the brain to solve problems in AI. This is not all my work. Some of this work was done before I joined Sandia, and some of these things are work I did with my colleagues. I've captured all of them there, and you might be able to tease this apart if there are questions that I will answer some things in great detail, and other things I'll be like, I will get you a link to my collaborator. Right, so we'll see how that goes. Okay, yeah. Let's wrap the initial story up before we go on. You could take those threshold gates, these sort of macular pits, neurons, and do interesting learning. And this was work done in 1957. The perceptron was built by Rosenblatt. I was trying to recall that name. And it's a simple 3-layer network of neurons. It's kind of like only one layer learns, but there is learning. And so they have this camera, there's a sensor, they randomly connected to an association layer called the A unit, and the A unit goes to a response unit, and the A to S layer, there's some learning. A to R, the associative and the response layer has some learning. And he argued that this machine could do some sort of classification, that you could recognize characters and recognize numbers if you train this unit. And these learning was done by motors controlling rheostats, right? So resistances control how much current flows back and forth. And it turns out this learning law is basically, in fact, just linear recursive least squares method, if you know what that is from your basic stats classes. So you had this massive computer system built in 1957 that is learning, that was inspired by neurons. And at least one example shows that you could do some sort of classification. Here it is. We have a model of neurons. We have an ability to learn. Looks like all we need is scaling in size, and we should be able to build a brain. At least that was a hope. That's not what happens. We don't have a brain yet. We don't have an electronic brain. So what happened? Where did we go wrong? We'll find out. So this is how I've composed this thought in my mind. I'll try and motivate why we should look to the brain. And my hope is that when I make this argument, it feels intuitive to most people that says, yeah, this is why we should be looking to the brain, especially for AI. Right? Then we'll look at what it means to be inspired by the brain to solve problems in AI. And the way I've thought about this is to go through various levels of abstraction. So processes that the brain might take, certain features they exhibit, or certain coding schemes they might use, actual architectures of the brain, computational architectures the brain uses. And then going down to circuits that it may implement to solve certain kind of problems. And we'll take a brief detour into something called neuromorphic computing, a lot of what my department does. I won't go into too much detail in the neuromorphic computing and what a neuron really is. You have another talk next week, and my colleague, Suma, who will be talking about these two in greater detail, will hopefully be able to add some more thoughts there. Then I'll conclude with a word of caution. We'll do. If you have any clarifying questions as I go along, I urge you to interrupt me. If there's a larger, broader discussion question, then hold to the end is what I would prefer, but feel free to interrupt me as needed. Okay. So why should we look to the brain? The reason people try to build artificial intelligence systems is simply because we are fascinated with what natural intelligence can do. And we see that it can solve problems efficiently in ways we just don't know how to code a computer. That was the original intention to go. We'd like these, not just learning systems, there's more things that AI does that's not necessarily machine learning, it's a broader challenge. We'd like to be able to solve all of that. And I've tried to capture this class of problems that we would like to use AI to solve is this, what we call the autonomy loop. If you had an autonomous system navigating its way through the world we live in, an environment, there are various problems that need to be solved that AI could really benefit. Some things might be harder to fit in this image, and we will I'll give you an example. A nice example that will fit nicely is a drone that's flying around and solving a task. So it has some goal, we don't know what it is. It has some goal to solve within the context of living in an environment, right? So it needs to sense the environment, it needs to make sense of what the sensor signals are. I'm using sense a lot. And take in the goal and transform the goal within whatever representation it has of the environment. It needs to build a map of the environment. It could be a logical map on actual physical representation of how do I navigate this building, fly around this building, to say maybe if you're doing natural language processing, trying to understand something else in terms of what does it mean to construct a sentence and what does it mean to unravel what phonemes are here. So I'm trying to use map to capture all of that. Then you need to understand where you are within this map. Then you need to make a plan based on whatever goal you have. Then you need to execute this plan. So you need to act. This is the control loop. Then you need to sense again to see how far off you are, correct yourself. And there's learning and problem solving involved in every aspect of this that is really hard to solve, each of these blocks. Brains, on the other hand, solve this extremely well. By brains, I don't necessarily mean just human brains. Like insects solve these things efficiently well. They have much simpler circuits, but they solve all of these similar problems. May not do natural language processing, but they still have to navigate the world. They do so remarkably well. And by that I mean they have to solve this problem in an ever-changing environment, in an ever-changing, they're embodied, but the body's changing. The world around them is changing. Nothing is perfect. Everything is noisy, and everything is collapsing because biology degrades in a really fast thing. And yet, they do so efficiently and take very minimal amount of energy to do this. So we could all benefit from this, and this is one of the reasons why I believe we should look to the brain to solve this. And as I give you this example, hopefully it intuitively makes sense, right? I mean, brains have already solved it. Why don't we just copy that and solve it? And I think that's why it's a hard problem. What I'm going to do next is talk through a few different levels of inspiration and give you examples to motivate it. I'll either state what feature I'm going to look to and try to draw an algorithm from it, or I might actually give you a problem that we're trying to solve and see how biology can solve it, and we go back and forth. So the first thing I'm going to do is think about this question. Do we ever get new neurons, humans? Or are we all born with the same amount of neurons that we start with? Or do we just lose neurons as we go? Any guesses? We do gain them. This was not known until, well, I used to say recently, but we've known this for 20 years now, at least. There's a process called neurogenesis. We don't gain them everywhere. It's one way of doing plasticity, right? There's this notion of neural plasticity, which says that new connections might be formed. So you have two examples, the two neurons, that the connection between the neurons might strengthen or weaken, new synapses might be formed and all of that. There's also this is a very different kind of plasticity. An entire new neuron is actually showing up. Neurons die all the time, but in certain areas of the brain, we have new neurons showing up. It's called neurogenesis. There's certainly evidence of neurogenesis in mice olfactory, rodent olfactory bulbs. Certainly some in cerebellum, but that happens in early childhood in humans. And in hippocampus, at least, there seems to be some adult neurogenesis, which is fascinating to go. Adults gaining new neurons. It's a really expensive process, but we seem to be doing it. There might be some benefit there. And adult neurogenesis was studied by one of my colleagues in my department there for his PhD, and now he's one of the distinguished members in my department. And what he did was use his team to look at this sort of process where new neurons are created in hippocampus, which means something very interesting. So if you take a network and start inserting nodes, you're sort of increasing the dimensionality of what you can compute. So what sort of problems can you solve using that kind of mechanisms? So here's what they did, right? They started with an autoencoder task. The task is to learn handwritten digits. This is just the MNIST data set. For those of you familiar with machine learning, there's a bunch of handwritten characters. And the problem this is solving is takes in an input, it goes that way, up there at the top. And level 4 is a compressed representation of this digit. It's going to look nothing like what this digit looks like, but if you can train the latent layer there to encode this information in a very low dimensional space. What they do is you start with a minimal neural network, and you learn 7. And then you try to teach it to learn 4, but it fails because the network is not large enough. And then you add neurons to that slowly. This is the opposite of approach to what most neural network training is, which is you take a very large network and maybe you try to prune it down and say this distillation idea that there's some smaller network that captures most of the information. This is almost the opposite approach to say, start with a small thing, then add neurons, because adding this network is expensive, so you should do it in a principle slow way. Then it learns to capture 4, and you can do this by, this larger network has learned both 7 and 4, and you can slowly build on these things. It's a different approach to thinking about what your neural network is doing. The learning is slower, but overall you've ended up with a more efficient approach to building your network size. And depending on the application, and this is an idea I'll come back to over and over again, this might be useful if you have to deploy some sort of neural network that lives in the edge and a low power working off a battery, then you want to have things as small as possible while being as robust as possible. I'm going to go through a second example, a different level of abstraction. And this problem is, let's see, so spatial navigation is the task we were looking at, and we realized that rodents have this interesting feature called grid cells. And what the grid cells do is slightly different from something called place cells. So let me describe what place cells do first. Place cells in the brain, there are neurons in the place cells that fire when you're a specific location. So there's a bunch of different neurons. And if I'm this location, a certain specific neuron fires. If I go to a different location, another neuron might fire. And depending on which of the neurons fire, you know where you are in a spatial configuration. Grid cells do something. Here's a recording of a single grid cell. A bunch of different grid cells. You put an electrode on a single grid cell. This work, by the way, won the Nobel Prize in medicine. I forget when, 2008 maybe. It fires in a grid pattern. So I move around. If I'm in this location, the single recording of the neuron fires. I move to a different location, the same neuron fires. And if you record all the firing patterns, it is a grid. A different grid cell might have a completely different grid pattern, but it still remains a grid. So the idea is that you can collect the responses of all these different neurons that all have different grid patterns and superimpose them, and somehow the superimposition is going to give you a single location. It turns out if you do this coding right, you can actually recover where you are. It's a fascinating way to encode a larger map. And that's what we ended up doing. The problem with spatial navigation is if you're a drone flying around the country, you need to store the map, or you need to learn this map. And then as you're flying around, you might say, or walking around, whatever it is you're doing, you look to sensors and you look at features and say, I noticed this feature. If it's a unique feature, I know exactly where I am. If it looks like you're ever in Santa Fe, if you look at an Adobe building, it could be like, I could be anywhere. But then you need to somehow integrate some information to say, where exactly am I, sort of thing. You can capture these various grid patterns by 3 different values. You know, what's the spacing between these grids? How is this grid oriented in terms of an angle? And 0, 0, do you have a grid? No grid. And if you have no grid, what is the offset there? So there's 4 different values. You can uniquely describe a grid. And so we use that information to solve spatial navigation task. This is a digital elevation map, the area around Albuquerque, actually. So you might have height here, Sandia Mountains. It's useful if you're in Albuquerque and not in Kansas, because digital elevation maps provide useful information. We have a drone that's flying around that can sense the altitude in a given area. So you know what elevation what the elevation the ground is at that point. Of course, there's contours. There's some challenges there that you have to think about in this. I'm sacrificing detail, rather focusing on the inspiration, neural inspiration to solve the problem here. Okay. So what we do is then use a bunch of different grid patterns that we're going to use to capture this map information. We overlay this grid, right? So each of these grid on that map, they look like that. And if you have enough of these, then we argue that you could capture this entire information here. And turns out you can decode where you are based on that information. It's called we've done some transformation. We've fixed the spacing between the grid and the angle which the grid rotates for every contour. So all areas that have the same elevation information has this one fixed pattern. And then within the locations, what you do is you capture just the face information. So the different points along the contour lines have different face information. So now if you sense an altitude, you kind of know which contour you're on. And once you have that information, all you have to do is resolve where you are along that thing. And we use this face information to have multiple cells fire. As you fly along, these firing patterns keep changing. And if you integrate all of that and you start superimposing some of this, in this case, we have 30 different grid patterns firing. You can almost uniquely resolve where you are. This is an extremely inexpensive process. Once you have this firing pattern, all you have to do is just superimpose all of them, do a simple addition. When different grids don't have matching firing, they die out. There's this one location where they consistently always fire. When you do that, you quickly understand where you are. Right? It looks like this. I've gone to a higher dimensional space, which we have, but I've reduced the amount of computation needed to resolve this, which is opposed to, say, doing something Bayesian where you're trying to extract a feature information, you're trying to calculate a posterior probability distribution based on some initial probability distribution, do some sort of Kalman filtering. Compared to all of the amount of computation needed for that, this turns out to be an extremely simple resolving mechanism. And it can also store large areas of maps. Sometimes we need to store statewide or countrywide amount of information as you fly along. This particular encoding scheme, there's obviously challenges, right? If you're flying over the ocean, elevation information doesn't give you much. There are other information you might want to encode, maybe not elevation, but New Mexico is great. I'm going to pause for a second to see on two different examples. Any questions so far? Okay. Yet another example of a different level of abstraction of the brain. What I'm going to do here is first motivate the problem and then look to how the brain solves this problem. This is constructed data from real world data, but we've constructed the noise and all that. So we have something called a DR data set. It's open source. You can all download it. It may not be free, but it's available to everyone. Taken that information, we've created this camera movement, which is following this random walk, certain specific statistical process. It's not important, but the velocity of this camera is captured by that. There's object moving within this noisy image, and it turns out the object is really small, smaller than a pixel. It's moving really slowly. I'm going to play this video here. I can't see the object. My eyes are not the best eyes, but if someone else can see, I'll be very impressed. Halfway through the movie, there'll be a red circle that will tell you where the object is. And even after I tell you, I'll be very surprised if your eyes can capture it. But we want to be able to track this object. Think of it as I'm looking down from a satellite. There's this tiny drone flying around, and we want to know where that drone is. Yes, right? Okay. So obviously there's camera movement, there's things drifting, and somewhere in there is a drone flying there. And if you keep staring at it, maybe you'll see a slightly bright spot there, which is barely above the background there. The SNR is almost 1. The signal to noise ratio is almost 1. Slightly more than 1. We want to track this. The standard approach we've taken in machine learning, for those of you who've seen things like that, is do some sort of convolution followed by a recurrence, which is captured there. And you do some sort of spatial convolutions, which is doing a whole bunch of filtering to your image to extract features out, and then combining those features to see what you're trying to detect. This problem, for this particular task, it doesn't work well, because the object you're trying to detect, the only interesting feature is that slightly bright spot. What happens if you do spatial convolution is some sort of filtering or averaging. You're going to wipe this information out if it's very close to the background. But this won't work. The reason we do this is because it's computationally maybe cheaper to do some sort of size reduction first before we do temporal integration. The brains, on the other hand, do a lot of local temporal recurrence. So spatial and temporal processing is key to the brain, and the brain pays a lot of attention to time information. So this is a combination of a convolutional recurrent neural network where there's lots of recurrence within each of these convolution layers. So before you start averaging out, you start doing some sort of temporal. And you use far fewer spatial filtering information there. Okay? And it turns out if you apply this, you get some sort of success here. And you can actually even reduce some of the latter temporal processing and still maintain this information. And you can use far fewer convolutional layers needed. This is inspired by the brain in terms of what computing architectures is using, but it's still fairly well within the domain of machine learning, right? You can do this you don't need specialized hardware for this. You can run it on your computer. And you get some interesting results. I apologize for the coloring scheme here. These look white. They should have been copy-pasted from a different slide. PowerPoint is intelligent in bad ways. So 3 different applications. This is your standard approach. And you'll see what the results are. Then we'll see some spatial temporal processing and then just shallow temporal processing followed by spatial. We'll look at how the results look. Ignore that for a moment. Focus here for a second. If you do spatial and then temporal, the longer you train, you don't see any benefit. This is mean squared error, so lower is better. You want to be as low as possible. You hit a baseline. You can't do any better. And if there's no recurrence, it turns out it does almost better than spatial. I've not been quite able to explain that gap yet. But it's not a big gap. It's just a logarithmic scale. And once you start going to sub-pixel accuracy, there's no way this approach can ever solve this problem. So there's a fundamental limit there. But if you start taking one of these approaches, if you do spatial, then spatial temporal, the temporal component allows you to go below sub-pixel accuracy. And if you do some shallow spatial temporal or one of these two, then you actually manage to get below sub-pixel accuracy. So here's a success story of looking to the brain at the architecture level, but then applying it to standard machine learning. And what we did next is, rather than use you have your neural network, which is this, with all of these neurons in them. And each of these neurons have activation functions. They could be ReLU, which is just everything that's negative is 0, everything that's positive you keep as is. Or you could have something like more complex, like tanh functions, or you could have threshold gates, whatever it is that you use to encode your neural network. If you replace some of those with certain interesting neuronal models, you start getting more interesting results. And we'll come back to this a little later in the talk, but neurons are not activation functions. They have both spatial and temporal components to it. They're dynamical systems, if you will. And a neural network in the brain is a combination of interacting dynamical systems as opposed to your standard neural network, which is, especially if you have no recurrence, right? It's just a bunch of functional approximators. If you have some recurrence, maybe you're capturing some dynamics. This is each discrete time step versus real time. So there's also that difference. But if you start capturing some of the interesting neuronal dynamics, which is more complicated than a threshold gate, if you have something like integrated fire neuron with some leak associated with that, so leaky capacitance, then you start getting much more interesting performance, and you can get sub-pixel accuracy fairly quickly. So that's another combination of using an architectural inspiration and a neuronal level modeling inspiration, combining those, and as low as 50 training epochs, you're already outperforming anything that your standard neural networks can do. And of course, training gets slightly more challenging when you don't have these simple activation functions, and you have dynamical systems, and you have to do backpropagation. So for those of you who've taken some neural network training classes, all of these terms will make sense. But for those of you who've not seen that, this is simply how we think about learning when you start adding complexity in the neurons, right? You can't use your standard machine learning tools, and you may have to rethink those. I think it's the takeaway lesson. The one more before we go to neuromorphic computing. What we have here is looking to the dragonfly brain. This was interesting for several reasons. It's solving a guidance problem, right? So the dragonfly is trying to capture a prey, and the prey is flying around, and you can see this little dot here. There, up top there's this little fly, fruit fly. Dragonfly is trying to capture it. Dragonflies are fascinating. They can track this prey really fast, and the entire neural network that does this is entirely understood, is fully understood. So we can look to this and mimic this. It's really shallow. I'll show you. It's only 3 layers deep, and it can start solving this problem in millisecond scale, which, if you think about what each neuron is doing, each neuron is working around 10 milliseconds, and then in 30 to 50 milliseconds, this guidance problem is solved by the dragonfly. And the guidance law tells you what trajectory you should follow to reach your prey, right? We know what the circuit looks like, so why not mimic it? The calculation of this guidance law is simply coordinate transformation, because dragonfly eye, in the eye frame, you see your prey, you identify the prey, and you want to know if on this image plane I see this prey here, where is the prey in the real 3-dimensional space? There's a bunch of matrix multiplication that needs to be solved. That's what it is. If you've done any graphics or robotics course, something you can do in a sheet of paper or two, you can calculate this out. But it's a fair amount of multiplication happening there, and you need to do this as fast as possible, which dragonflies do. There's no learning involved in the traditional sense of machine learning. Dragonflies are born with this. This is hardwired. So solving an AI problem, but not necessarily a machine learning problem from dragonfly's birth. But the way these nervous system network, the neural networks, have been calculated is learning through evolution. So it's a different time scale, though. But it allows you to understand what kind of fundamental problems these neural circuits can solve. They can use these to build more complex things. So this is what a abstracted out dragonfly circuit might look like. It's there are 2 pieces of information that go in. Where your head is, you need to understand your internal state. Where on the image plane your prey is, so you get a 2D piece of information. And you need to combine that to understand which direction you start flying out. And the dragonfly circuit can calculate this in just these 3 layers. Simply a weighted sum followed by some simple nonlinear transformation. It's standard neural network stuff. And this is entirely known. So again, this is pre-calculated weights. The weights are not being learned. It's understood. All these different papers have that information. You can go look this up and implement it. This is open source code if you want. So what does results like that look like? What you see on the right bottom, let's start here. Right bottom is this is the dragonfly's body, and this is the I-frame coordinate system, and the projection of the prey is somewhere there. All the dragonfly is trying to do is turn its head and body around so as to try and keep this prey as close as possible to the center. Slightly more complications there, because if you're flying faster than the prey, this is an extremely successful strategy because you can do pursuit behavior and capture it. But if your prey is faster than you, then you need to be forward-looking, right? You need to start doing predictive coding to say, my prey is flying in that direction. I need to aim there so that by the time I reach there, I can intercept it, sort of things. So obvious national security applications there. In the top right, you see what the actual thing looks like for an observer from outside. The black is the dragonfly, the red is the prey. The simple example, the prey is it's a straight line shot. Dragonfly is faster than the prey, it does so, it pursues. The circuit can also calculate future, like a predictive coding scheme, and it doesn't have to keep this at the center, but it needs to calculate one extra transformation that says, I'm moving so fast, what is that extra rotation matrix computation? You can do something similar and solve that problem. Okay. All the examples I gave until now, maybe except for neurogenesis, you might rightfully argue that, let's look at the perceptron, right? The perceptron did linear least squares. We know how to implement linear least squares. The dragonfly did coordinate transformation. We know how to multiply matrices. We did the grid coding, maybe look like a weird way to encode your map, but there are other ways to encode the map. If you give me a computing architecture, if you give me a standard computer, there's almost a better way to do this, and this has been an argument against neural networks for a long time. It almost killed the field a few times, but there's always one nice problem that neural networks can solve that your traditional algorithms cannot solve, so they always has a revival. We'll see how this goes. So if you can always do all of these computations in a more efficient way in your system, why then should we be looking at what algorithms the neural networks, the brains use? The answer to that is because the human brain, in this case, and any biological brains, do it wonderfully well, other than being extremely noisy, working in extremely noisy environments, and also doing highly parallel computation. It also takes very minimal energy. Human brain takes less than 20 watts of power. Remarkable for all the problems it can solve. Compare that to your an i7 Intel processor. I'm not entirely convinced that this is the numbers we should be looking at, like transistors, or should you be looking at gates or transistors? What is the fundamental unit there? Maybe it is gates, right? Maybe it's the threshold computation. Maybe it's your logical switch. 1.4 billion versus 100 billion, it's a lot more here. And then it's extremely parallel. That's not how your von Neumann architecture works. There are different architectures. And it's self-organizing. It's changing all the time. It learns. That's kind of fixed. So could you then build a different computing architecture that's inspired by what the brains do? And this is neuromorphic. And there are various details there I've conveniently washed out. It's really hard. These things are in 3D. We don't know how to build things in 3D. It's the different types of neurons. They're extremely highly connected, and we had some discussion on connectivity, local connectivity versus connectivity at distance. There's some interesting scaling laws there. When you put together a bunch of neurons, there's some level where emergent behavior starts appearing. There's a few more complications that I will talk in my last slide, but you can build brain-inspired computers. In fact, at SND in my department, we have one of the largest collections of these new hardware. The other point that I want to make is we may not have a choice, but to start looking at different architectures, and this is one possible architecture. The reason being is the way we build these kind of chips is we're hitting a wall. You can't go smaller, you can't go faster, you need to rethink computing. And so one way to do that is look to the brain. And there are other alternative approaches as well. Quantum computer is one of them, or you can just do better modeling there and maybe shrink a little more, but eventually you're going to hit a wall. Physics is going to limit you. So if you had a neuromorphic architecture, a computing system that did not look like that, then some of the algorithms that I've talked through before will naturally fit in here. It turns out this is a very efficient implementation if you do that kind of AI within a neuromorphic. So that's my takeaway from this slide. And programming these things are very different. It's not your imperative, it's not your procedural programming. Data flow architectures may be perhaps a good way to capture this, but it doesn't fully capture, and I'll comment on that towards the end. There's some interesting computer science questions there as well. So a lot of advantages to looking at neuromorphic computing, and the primary argument is that extremely low power, and you can solve AI tasks in much orders of magnitude lower power here. And if you increase the complexity of neuromorphic computing, then maybe it will get us to building an artificial brain. Going back to the original problem with perceptrons, maybe there is a path forward there. And next week, I believe Suma will talk a lot more about neuromorphic computing, right? The primary fundamental challenge is that we already have some neuromorphic computers, some of which down the road in Albuquerque. We have the same number of neurons as, say, a mouse might have, or a dragonfly might have, but we don't have a dragonfly brain or a mouse brain. And there is a problem there. The reason we don't have these brains implemented there is neuronal complexity and certain connectivity issues, and of course, three-dimensional versus two-dimensional. The primary challenge is neuronal complexity, which is going to be my last slide before I end this. And I want to maybe push for this point here to say that you may need a complex architecture to benefit from real neural-inspired AI algorithms. Quickly, what the challenge with the neuron modeling is that most of the way we do this neuronal modeling now is integrated fire, IF models, which simply says accumulate information is bigger than a threshold. And then we capture all of the synapse or the connection information as simple weights. That's it. We miss all of the rest of the neuronal modeling information. And these tree-like structures called dendrites do a lot of sub-threshold computation. They solve coincidence detection, context-dependent processing, some nonlinear summation. They do multiplication, and it's like your retina is full of sub-threshold neurons. By the time light impinges on your retina and goes to your visual cortex, it's done a whole bunch of computation already that we just conveniently ignore in our modern engineering. So if you were to capture all of that, which is much harder, and doing analog computing, then you could start doing a lot of stuff. And this is where, in my mind, research is heading for brain-inspired AI and why we don't have a brain yet. There's interesting questions you can ask. What does learning look like if you have these complex neuronal models? What else would the specialized hardware require? Analog computing together with digital computing mixed together. How does that fit in an HPC system, for example? How do you program these things? And now you're suddenly talking about a bunch of dynamical systems interacting with each other in a very large scale. How do you design these things? How do you engineer these things? How do you implement an algorithm in this? It's fascinating questions. How do you program this? How do you express an idea at a higher level and translate it down? Open questions, fascinating questions to me. And all of this is some nonlinear interaction involved in there. And it has to be both spatial and temporal components that's being used to compute, right? So a rich source of research problems. So, a word of caution, and I will end it here. What do you see here? A face. You know what this image is of? It's a rock on Mars. History Channel will tell you this is evidence of aliens, right? Maybe it is. I don't know. I don't know if that's the simplest explanation. It's a captured image. But the problem here I want to highlight is that human brains are tuned to recognize faces. The reason why, if you see ink blots, you see faces, because human brains have a bias. It's not just unique to human brains. Natural brains have evolved through evolution, this evolutionary pressure that shapes them. Recognizing faces is a good thing. Recognizing certain things that maximizes your survival, finding food, is all good things. And so you bias your solutions toward that. So the word of caution is if you're not careful and don't fully understand how these architectures evolve, you would end up encoding all of these biases. So you want to be really careful. And then you need to understand how much of the information to abstract, what layer to look for. understand what the applications are, which of these things in the brain are relevant to an application, which are not, and what are the constraints under which the brain designed this algorithm, and what are the constraints we're working with. They may be very different. You need to engineer that right. So the way around it is to think about co-design, where you're designing the algorithms, the hardware, the applicational constraints, and all of that from device level to architectural levels and above simultaneously. It's the opposite of how we do engineering. We do top-down. Someone gives us constraints. We design to the constraints, and we program to these things that we've designed. Rather than do this linearly top-down, the way to do this is to do this sort of circular. Everyone talks to everyone else in design systems. It's a much harder problem, but that might be the only way out. So that is all we have time for, and these are the things we talked about today. And with that, I'll take questions, and I'll stick around longer if you want to have a chat. Email there. I will be fairly responsive, and I will connect you with the right people if there's any specific topic that you'd like to know. Thank you. Yes. Oh, I didn't realize you already had those questions. I thought you were waiting for this. Okay. Yeah. Yes.
So you ended this, we should have this engineering, or essentially engineering.
Mm-hmm. Mm-hmm. Yes. 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 It's really hard, right? I mean, it's hard to test your designs. That's why we don't do it. If you do a top-down approach and someone were to constantly tell you your design should fit these restrictions, and then so someone gives you requirements, you use that to come up with a set of design constraints. And then someone takes the design constraints and proposes a design, and then you optimize within that. If you take that approach, it's very easy to constantly test at every level to go, do I meet this criteria, yes or no? If you start doing co-design, there is no framework, because what is the suggestion here? I can't solve a problem. Do I need to change my materials that do the device, make the device work? Do I change the device structure? Do I change the circuit with my device? Or is it a combination of these three, and where is my cost-benefit analysis? It's a more expensive approach, but there are certain situations where we certainly run into that at Sandia National Labs, where this is the only way out. So we have, I think, an informal technical know-how to answer your question of how we might be able to do that, and it's a very painful approach. So I wish there was a formal textbook, if you will, that tell you this is how you would go about doing co-design, and we're hoping that this will come out eventually. But again, that's also another research question. Like, how do you teach someone to co-design is something we all, I think, struggle with. It's learning to understand other people, even if you're engineers, right? A material physicist talking to an electrical engineer, talking to a computer scientist, they all speak different languages. Worse, they use the same terminology to mean different things. And then you have to somehow circumnavigate this situation. And I think that's a very useful skill to develop in the world we're moving. Yes, sir. Yeah. Okay. If I captured your question right, I started the talk, the early quote from 1943 talked about the all or nothing behavior of the neurons, which is essentially a threshold gate. It's either on or off. The question is, are there other organs that do this all or nothing sort of thing? Or are there other mechanisms other than all or nothing that we could be using? Right? Fairly capture that question. Hmm. Okay. So are there other organs within your natural systems, biological systems that do this sort of all or nothing? Um, I'll take the first part. The all or nothing thing described early on, 1943, is the threshold gate. It actually turns out to be the wrong model for neuron. It actually, if you look at a neuron, um, there is no specific threshold. There's a lot of stochasticity, and these thresholds keep changing and all of that. And something I intentionally ignored my entire talk is how stochastic the brain is. It actually, I believe, it leverages noise to compute interesting things. I digress. Um, the There are certain other organs that we know. The muscle, for example, does spike and converts spike to linear motion. There's some all or nothing computation going on there. But most of biology is not this rigid all or nothing switch stuff. So I'm going to argue against the point. I try to motivate this and say that was the initial inspiration that people used to build neural inspired computation, but it's not how biology works. In fact, towards the end, hopefully I've made the point that the neuronal models are a lot more complicated than just all or nothing. In terms of are there other organs that might be using something similar, I don't know the answer to that. Yeah. Yes, sir. E yes. Okay, so can you look, so the question is, are there other uh, places in biology that you can draw inspiration from other than just the brain? Is that a fair summary? Hmm. Ah, okay. How do you mimic a biological organ that is okay, um, that is not like your machines, which are all repeatable, fixed, rigid components? It's an extremely good question, right? People spend entire careers in just building neuronal models, for example, and other organs of biology, like how does the cells in your heart work? What are the mechanisms in your cells? What's happening with your musculature? It's changing all the time. So how do you model these things? The typical approach people take is to a data-driven approach. You collect a bunch of data, you try to fit an interesting system model that follows it, and you either ignore time and say, here's a static model, or you say, I'm going to incorporate time, and now I have a dynamical system model. I can simulate this perhaps, and I need an HPC system. It's too complicated. What do we do? Someone else builds an entire career taking this really complex model and reducing the complexity until they simplify stuff. And so you observe something simple, build a complex model, simplify this, and end up with something completely different from where you started at. Hopefully build something. That's our current approach. Is it being useful? Some parts, and there are other places where I think we just fail. So there's some thinking that we need to collectively do to see how do we leverage all of this, I think. Yeah. Yes. Yes. The, yes. And people have strong opinions on whether they should have won the Nobel Prize or not. Yeah.
So, but it's great to be down the street.
Thank you for the invitation.